Okay. Can everybody hear me, or how is my voice coming there? Good? Okay, great. I think my talk will be a little bit more technical. I hope you had healthy dose of coffee after the lunch. I'll try to, for this talk, please ask questions while I'm talking. I guess after the talk, it may be too late. So if you have any questions, please interrupt me. I would like to, explain the things. But I mean, I probably will not remember most of the things I'll tell after this talk, but just remember that there are so many cool technologies out there that many things you think may violate privacy or security could be done actually without violating those. So in the next, how many minutes, 20 minutes or 25 minutes, I will try to convince you with that respect. So the choice usually is not between the privacy or the utility or doing things, but whether you would like to pay the price for the privacy. But in most of the cases, probably you can do whatever you want without violating the privacy. Of course, there's a cost associated with it. So that's the main premise of this talk. And I'll talk about some technologies and some of the things that we are doing and the existing tools out there that can enable this. Okay. And one of the challenges, Brett has done a very great introduction about what's the field and what's going on, is to really integrate multiple data sets in a, let's say different hospitals may have different DNA databases, different patient and genomic and phenotype information combined together. And the goal is, I just put NIH here, it could be other data integration sources. The goal is to really integrate this data and to do something useful with it. And of course, as a researcher in data security and privacy, the challenge is because of the highly sensitive of this data you are having, how are you really going to integrate these data sources? How are you going to store this and query them without really violating privacy? And what I'm saying is there are many, many cool technologies out there, especially privacy-enhancing technologies, that can help you with many of these challenges. I'm not going to go into too much details of them, but basically, in order to protect against like some hacking or someone getting your computer and running away, you can really store everything encrypted, like using symmetric key systems, which is not costly, I mean, in terms of computation time. So you can store everything encrypted easily. And there are many tools that are like standard corporate now laptops are coming with encryption technologies that encrypts the data. There are public key systems. Probably you are using public key system if you are doing any online transaction. So these public key systems, basically, the person who encrypts it, there's a public key to encrypt data and a private key to decrypt data. And this is commonly used. And as I mentioned, if you've done any online transactions, you use the public key system, basically, built into your computer. And on top of it, there are other new tools and techniques in crypto, which we try to leverage for one of our projects. You can encrypt the data. Encryption basically make sure that you don't reveal anything about the data set. But still, the encrypted data could be manipulated somehow to do some useful processing. So in other words, without looking at the data, you can do something with it and get the final result. The example is, assume I would like to learn the average age of the people here, okay? So the obvious thing would be is to ask your ages, which I assume will not be privacy preserving, at least if you don't want to reveal those. And the other option is, by using these cryptographic techniques, I can get the encrypted ages of everybody and then aggregate them and just decrypt the final result, just the average age of everybody here. So in other words, I can learn the average age of the people here without learning any single age, okay? But of course, here, for example, if this crowd is college students and if the average age is 35, it may say something about the participants. But still, the point is by using this technology, I can learn the average age of the people in this room without revealing any single individual age. So that's how, I know it sounds like magic, how you do this. The math behind is complicated. I have 3 slides for it, but I will pass away. Don't worry about it. If you look at the next slides with the math on it, I will pass them. But basically, this is doable, and there is so much things behind, and there are some other tools there. One particular tool that I find it interesting is there are, for many, many years, there are some cryptographic hardware. So in other words, the keys and the other things that you need for this kind of secure processing can be now cheaply stored on some secure hardware. And these hardware do some additional, have additional capabilities. So there are many cool technologies out there. On top of it, Brett talked about anonymization techniques. So you can combine cryptographic techniques with the anonymization techniques easily, and I will briefly mention how in one of our techniques we have done this. And on top of it, I think one part of this thing is access and preventing wrong people to get hands on this data. And the other issue is, especially if you give access to others, accountability could be a useful tool. And there are many techniques now about secure audit logs. So like you can use these crypto techniques and this secure hardware to create logs that's almost impossible to manipulate or change, for example. So you can have such log systems there. One thing that I forgot to put here is there is some digital rights management tools out there. So you can ship data to some location. Like you can send software, and actually now software companies, and if you have iTunes try to use such a technology so that you can download, let's say, music piece, but you won't be able to play it in some other computer. So you can apply such things for data sharing as well. So you can send data to some location, but using these technologies, the person that you send the data with may not be able to copy it to other device, for example. So overall, there are zillions of technologies out there, and what I'm saying is most of the, and these enable you to do some interesting things. One of the things I skipped this, okay, sorry, my bad, so I have some things. Although I was warned about that no math, but sorry, skip them, okay. So we have done an example, so we try to use these technologies developed by cryptographers for the last 10, 20 years, and even 30 years, and to apply this framework. And many of the attacks the Brett has described could be possible by having an access. Not all of them, there are some attacks can just use the aggregate results, but most of them were using specific access to individual DNA sequences or individual genomic sequences. So we try to come up with an idea, and here, when we were designing the system was, we don't want a single point of failure. So we don't want, if a hacker hacks into one system, just one system only, and everything could be lost. So we try to come up with a mechanism where at least you need to hack into 2 systems. So, I mean, why 2, you may ask? Actually, you can expand it, but the more systems you have, your security increases, obviously, but the cost increases as well. So we just do it with 2 at this point. But basically, if a hacker, so we divide it into 2 sides, basically. One side will hold these keys to encrypt the sensitive data, and the other side has the data that's encrypted. But this side doesn't have the key, so it cannot see the data sources. It just has encrypted data, and because of the security of encryption, what the side sees is just encrypted data, which means nothing to this side, under, again, some assumptions. And this side doesn't see the data, although it has the key, but it doesn't see the data. And by using other technological means, we can share this key among multiple sites if needed to make it even more secure, but it will be more costly. And then what our framework and vision is, each hospital using remember there were some systems I mentioned that can have public and private key. So the key to encrypt data could be given to everyone. but the decrypted data should be kept private, okay? So in other words, you can give this key to all the hospitals, and they can encrypt their data with this technology and send to this central site. And remember, no one here has the, this site has the key to decrypt the data. And I hope it's, how many people is lost at this point? I just wonder. Please be honest. I'll try again. Maybe some of the people. Anyway, I mean, I'm trying to say that basically no one, there are no person who sees either the data and the encrypted data and the key together. So this site has just the data. Of course, these guys already owner of the data, so they sold it. But this site doesn't have the key, and this site doesn't have the data. And then what the slides that I skipped, this specific encryption scheme that I didn't describe, what it enables is a scientist can issue a query to this data site. And this data site does some processing on this query. Remember the example I gave? So I can compute the average of the age of the people in this room without revealing individual ages on the encrypted data. So this site can do such a processing, okay, and send the result, but just the result, okay, encrypted version of the result. So I assume I have your encrypted age information. I do the processing and I compute the encrypted average age, but I don't have the key. I can't even decrypt it. So I send this encrypted result to the site that has the key, and then that site decrypts the result and sends to researcher. So throughout this process, no one sees individual DNA sequences, okay? And if a hacker hacks into this site, this DS site, it won't be able to learn the data. If it hacks into this site, it won't be able to learn the genomic sequences. You need to really hack into two. Of course, one of the attacks, the Homer attack that Brett mentioned, works on aggregate statistics. So you need to be careful about what kind of queries that you are answering. Like Brett mentioned the study, like you shouldn't answer some correlation related to some certain SNPs. So this is not solve everything. So, but at least you can do most of the processing in a secure way without seeing the individual genomic sequences, okay? And this idea could be integrated to do data integration. If you attended in the morning Stanley's talk, Stanley gave one example of how to do privacy-preserving data integration. Our framework has a different variant of it. And you can really encrypt these data that you have from different hospitals, and you can somehow integrate them, okay? And also, and this process is somewhat slow, and we have done some experiments. In order to make it faster, we are using this k-anonymity that Brett has mentioned. Basically, let me show an example. So assume you have some data set that you would like to match, okay? And we have some technology or encrypted techniques to do the matching, but itself, this may be slow. What we do is, instead of revealing the individual data, we reveal a two anonymous version. And the idea here is these two anonymous versions, if you look at it, these two individuals are indistinguishable from each other, okay? So what we also do is, as a part of the system, we use this kind of anonymized data to do the initial blocking. In other words, instead of comparing all this, like this encrypted data, and this was mentioned in the morning about like you don't want to match like 1 million records to 1 million records because you will have 1 trillion and so on. So instead of checking for each pairs using this encrypted data set, what we can do is use this anonymized data. So we use the anonymized data to say that, okay, for example, this two pairs, I mean, these two tuples may match, and these two may match, okay, because they are similar. Okay, but we know that maybe this two doesn't match because they have different age, okay? So we can use such anonymized data and so to make this process even faster. So this is what I mean at the beginning, like combining cryptographic techniques with anonymization techniques. So we use the anonymized data to reduce the number of cryptographic operations that we need to do. And so therefore, what I'm trying to say is you can also in this framework, you can integrate different data without seeing individual data entries, but either the anonymized version or the encrypted version. And we have like proofs of security, and we also analyze what this brings you in terms of privacy. And there are other issues that we are designing. For example, we would like to be able to do audits. Remember the querying done in this data, in this framework. You may do audits. In other words, whether some certain policy has been followed or not, without revealing all the people who has queried these data sets, database or data or system. Also, you can preserve the privacy of the individual records again during this audit process as well. You will only reveal the persons who violated the policy, for example. Of course, our system cannot support all or any imaginable policies, so we have a restriction on that. But still, you can do audits on that. Of course, this comes at a price. I mean, like you can, at least for me, it's all these cool things. So the question is, what's really, what are the limitations here? The main limitation is this is significantly slower than a non-encrypted version, because the encryption things that we are using, the sophisticated techniques we are using, are much more costly in terms of computation time than the non-encrypted versions. So it takes longer to do this kind of analysis. So it's slower, okay? And because of the security needs, you need to store more information. It's because of the key sizes and so on. So the amount of storage increases. I'm not that worried about the storage because storage is getting cheaper and cheaper. So, but I think the more issue is about computation is also getting cheaper, but still these techniques are few orders of magnitude slower than non-encrypted versions. So that's what we are currently working on. So I try to give an overview of what kind of techniques out there to do privacy preservation in storing and querying genomic data, and try to give an example by discussing one of the systems we developed. There are a few others, but similar in nature, I would say. But so the point is you can do most of the tasks you have in mind without violating privacy. And I think the real trade-off is really between the cost in terms of like the building this system will be costly, the computation time will be maybe more than non-encrypted or non-secure version, okay? But almost, I mean, there's a nice theory behind, and there are many tools out there. Almost any computation you had in mind on any sensitive data could be done without revealing the individual data itself, like individual entries. So you can get all the aggregate statistics, all the aggregate results you want from any set of sensitive data without revealing the data. Therefore, the data is not really the, I mean, the privacy may not be the bottleneck. It's more like the cost associated with it. So this, I conclude here. I'll try to, and these are some of the papers that we have written on this. So I will stop here and answer some questions. Yes?
Two questions.
Sure.
First, if I understand what infer, when you said that you can compute the sum directly off the encrypted data,
yes.
The implication is that somehow you figured out an nifty encryption methodology that preserves the data from the point of view of certain mathematical operations. Does that include, for example, running a logistic regression? Yeah,
actually, that was my my PhD thesis was how to do data mining algorithms on such data. It's called privacy preserving data mining.
That's really nifty, and I'd like to learn more about it.
Yeah, I mean, I have 3 slides on that. Actually, cryptographers now recently developed even more sophisticated techniques. You can do almost anything on encrypted data. I mean, any computable function. I don't want to be technical, but you can do any techniques that you imagine. But still, the results itself may need to be protected. So in a sense, like, I can learn the average age of the people here, but average age itself can reveal something sensitive. So there's still, but you can come to that level. That's what I'm saying.
Second question.
Yeah.
I come from a national statistical office, and while you're discussing it, and Brad Mallon before you in the context of genetic data, we've been worried about this for years in terms of social science data. And people play with data blurring, for example, and data suppression in order to construct public use microdata files. But the thing that a number of statistical offices are doing these days, and the question is, have you looked at it, is we'll call it real-time remote access. We basically take the standard statistical package and put a software wrapper around it saying we're only going to allow certain commands coming in to be executed, and we'll be a little bit relaxed on the incoming, but on the outgoing we're going to strip away maxing in or whatever it could be identifying. Where is that kind of strategy in this overall landscape?
I mean, there are some techniques that I didn't discuss. There are like something called differential privacy. So people try to add noise to these results itself, so that the results will not reveal will not violate individual privacy. So there is so much work on this data area, especially going back to maybe 30 years back, about statistical database security. So there is so many people think about what kind of privacy issues are there when you are releasing some data sets. And in our case, we thought that it will be harder to limit the results, but the potential of audits and threaten to sue you or something if you misuse the data later on. So you would audit the queries later on by automated means and see if someone has violated it, maybe. Though the auditing itself is a tough process. I mean, you won't be able to audit against all the attacks, but that's still possible.
Also, just a simple answer also to your question, another one, is that if you can wrap the crypto processes with your policy mechanism. So let's say you do a computation, find the max is too large, suppress it, don't respond. So we're able to do the computation, but I don't have to answer your question at the end. So there's a whole series of policy wrappers that have to go on any type of cryptographic model.
Sorry. Yeah, right. Sure.
Multivariable analysis, so we're not just using one variable to predict.
Yeah, you can do multivariate. It's yeah, and there are some work done on the multiple regressions and so on already. So we haven't done for genomic data. For genomic data, we have tried for correlation type of analysis, but you can do multiple regressions on that. I can give you some pointers, but I just want to warn there is some crypto behind it that needs to be. But yeah, I would be happy to discuss offline and give you pointers. Yes.
The same researcher does several questions to this encrypted database. Like over time, maybe this set of questions might be able to reveal something, right? So
Yeah. So the question is, assume I ask multiple queries. So for example, I asked the query of people who are, average age of the people who are from Canada in this room. Then I asked the average of the people who are from Canada and who are female. And by asking a series of such aggregate questions, then I can pinpoint your age, for example. And this is possible, and that's the worry about how to do it. There are, at this point, emerging, I mean, this was called in the database community statistical database security. So over the last 30, 40 years, the main things emerge out of this is try to follow queries so that after a certain point, I won't answer your query, but this turned out to be harder. The other thing is add some type of noise to each query so that the queries are not exact, so that when you try to combine them, you won't be as successful, okay? So I would say there is this two kind of approach out there. But by my discussion with Brad says that the people in medical domain doesn't like noisy data, so they don't like to add some noise to the query result. So that's the reason we didn't suggest the noisy approach. We suggest to do the auditing approach, so that if you misuse the data or try to do something bad with it, we will try to catch you. But of course, you can theoretically find a case that, I mean, the harder part is now we can catch individual people, but now 3 people can call it, your friend, yourself, and ask the queries individually. So it's, there may be some issues there. But, theoretically speaking, you can assume that all the queries issued to the system, in the worst case, issued by one person. But in that case, then after a point, you won't be able to answer any queries, because it would be really a worst case scenario.
But I mean, a mathematical model for auditing.
Yeah, mathematical modeling, in the worst case scenario, you may assume that all the queries issued to system is issued by just one person, and do the auditing for one person case, as if all of them are just one. But in that case, you will stop answering queries pretty soon, because let's say if 10 or different researchers ask different queries, after a point you will find a case that there's an intersection of one people in all these queries that can be really revealed, and you will stop answering. So that would be tough. But so what I'm saying is we tried to solve part of the question. Yeah, you have one more question?
Well, now we'll turn it to Kana, because you just answered
Okay.
it, which is that if you're not willing to randomize the data, a data set has to be thought of as a non-renewable resource. It can only sustain a finite number of queries before residual disclosure becomes virtually certain.
Mm-hmm.
I'm not sure many people appreciate that, because there's a serious trade-off.
I mean, at least I would like to just come to the sorry. Finish. I will just come to the thing of what Brett says, the risk modeling, and that's what I'm trying to do. I don't think all of the, there is the worst case scenario, obviously, like 10 people collaborate together, have the Intellis data, all the public records, and then combine it with some other resource, and then do a super duper attack to do this. But I don't know what's the likelihood of that versus the risk of or the cost of not answered queries after some certain point. I think we need to have some more research to balance that risk versus the utility there at that point. But my main point was you can get all the aggregate statistics without seeing any individual data. That's the final thing. So I think we ran out of time. So yeah. So thanks. And
there's a lot of ways.
Yeah.
So there's a lot of ways to answer